Alright, so this will be the first lecture over chapter 18. So chapter 18 is over aldehydes and ketones. So there's a lot of reactions in this chapter. So a lot to learn in this chapter as well. Okay, so in this lecture we're just going to look at how to name aldehydes and ketones, review their general properties, and then also review how to make aldehydes and ketones, because we've already seen lots of reactions that make aldehydes and ketones. Okay, so first of all, how to name them. So if you remember, an aldehyde has a hydrogen on a carbon-oxygen double bond. So to name it, so 1, 2, 3, 4 carbons. So the parent would be butane. To name an S an aldehyde, just change the E ending to AL. So that would be butanal. So you don't have to say butan 1-al or 1-butanal, because by definitions, aldehydes have to be at the end of a molecule, because it's got to have a hydrogen at the end, so there can't be another carbon there. Okay, so to name ketones, so ketones have a carbon-oxygen double bond right between 2 carbons. So 1, 2, 3, 4, 5. So 5 carbons would be pentane. To change it to name it as a ketone, change the E ending to ONE. So this will be pentanone, and you have to specify where the double bond at, right? Because that's also a 5 carbon chain, but that's obviously a different molecule. Those are 2 different ketones that are both pentanones. So this would be pentan. So put the 2 right before the ONE, which is what tells you that it's a ketone. And then this would be pentan 3-one. Okay, so let's take some more examples. So throw some more complexity in. So in this case, 1, 2, 3, 4, 5, 6. So 2 functional groups, aldehyde and alcohol. So now you have to know which one has priority. And again, the more oxygens in the functional group, the higher the priority. So the aldehyde has like 2 oxygens or 2 bonds to oxygens, and the alcohol only 1, so the aldehyde has priority. So what do you call OH when it doesn't have priority? So that would be called hydroxy if it doesn't have priority. So this would be 5-hydroxy. 6 carbons would be hexane. Change the E to AL. So that would be 5-hydroxy hexanal. In this case, we have a ketone, so 1, 2, 3, 4. So NH2 would be called amino if it doesn't have priority. So this would be 4-amino. Cyclohexanone. So you don't have to say cyclohex and 1-one because it's a ring. So by definition, that's where you have to start numbering at. Okay, so next molecule, so a ketone, and if you remember, what do you call benzene when it doesn't have priority? You call it phenyl. So 1, 2, 3, you want a number to keep the ketone as low as possible since it has the highest priority. 4, 5, 6, 7. So this would be 5-phenyl heptane. So change the E ending to ONE, and the double bonds at number 3. So 5-phenyl heptan 3-ome would be that molecule. So in this case, so that would be called cyclohexane carb aldehyde, is so how you would treat that, just the aldehyde onto a larger ring structure. Okay, so in this case we have 3 functional groups. We have aldehyde, we have alkene, and we have ketone. The one that has priority is the aldehyde, so that gets to be carbon 1, 2, 3, 4, 5, 6. So if an aldehyde or a ketone does not have priority, then you call it oxo. So this would be 5-oxo. So this would be 6 carbons, so that would be hexane. Change to make it an aldehyde, that E goes to Al. To take care of the double bond, that A goes to E. And we need a number right in front of it, say where the double bond starts at. But then the ketone is now a substituent, so that is a substituent on the 6-carbon chain. So that would be 5-oxo hex 3. So put the 3 right before the E, which is what tells you it's a double bond, carbon double bond, and then Al. And you don't need a 1 in front of the Al because aldehydes have to be at carbon number 1. Okay, so some aldehydes and ketones have common names that you just have to have memorized. So technically, this would be called methanol, but no chemist ever calls it methanol. They usually call it by its more common name, which is formaldehyde. So we'll see this form a lot the rest of the semester. So 1 carbon is form. And so this is 2 carbons, so technically this is ethanol, but most chemists don't call it that. Most chemists call it acetaldehyde. So we'll see this a lot in this class as well too, the 2 carbons acete being used instead of ethanol, instead of the F being used. So this one we looked at a couple chapters ago, right? That's benzaldehyde. So this ketone is technically 2-propanone. So I'll go back to the way I learned organics. So that's the way it used to be, right? But now it's more common to put the 2 right before the "-one", right before the functional group that it belongs to. But most people don't call that propan. You don't even have to put the 2 in there, right? Because if it's a propanone, then the double bond, C double bond, it must be at carbon number 2, because if it was at carbon number 1, it would be an aldehyde and it would be propanol. But most people don't call it that. Most people call this acetone, which is a compound some of you have probably used before, because that's what's in fingernail polish remover. Okay, and then this one we saw a couple of chapters ago, aceto. So there's that ACET again from the 2 carbons, just like we saw it here. And then this one is benzophenone. Okay, so just to review some structure and bonding, which we would have talked about in Organic 1. So first of all, important to recognize, right, oxygen's partial negative, carbon's partial positive, and that will affect the reactivity of the molecule. As we'll see, nucleophiles will be attracted right to that atom, and electrophiles would be attracted to oxygen. That's represented by a resonance structure of carbon-oxygen double bond, right? You can put the negative on oxygen, and carbon can be formally +1 charged. So in terms of physical properties, so if we had these 3 molecules, which one's got the highest boiling point, right? So the alcohol is 82.4 degrees Celsius, the acetone's 56 degrees Celsius, and the alkane is -12. So why the differences in boiling points? Well, because the alcohol can make hydrogen bonds to itself, and you have to break those hydrogen bonds to get the molecule into the gas phase. In terms of the aldehyde or ketone, they have a dipole moment, right? So if you had 2 ketones or 2 aldehydes, then they would tend to align themselves like so in solution, so that you had a dipole-dipole attraction. And you would have to break that electrostatic attraction in order to get the molecule into the gas phase. But requires less energy to break that type of attraction, so it's got a lower boiling point. And then for the alkane, it just has van der Waals. Which are the weakest of the intermolecular attractions, so that's got the lowest boiling point. So you see this reflected if we take this alkene, so 1-butene versus propanol. Right, about the same surface area, 4 heavy atoms, but the aldehyde has a dipole moment, right, 2.5 dBi, and the alkene is very nonpolar, only 0.3 dBi dipole moment. So about water solubility. So acetone is miscible in water. If you remember what that means, it dissolves in all proportions. And if you start adding carbon chains on it, so just add 1 more carbon, so 4 carbons, now it's only slightly soluble or partially soluble. So here 27 grams dissolves in 100 mils of water. So why does it have any water solubility at all? Because it can hydrogen bond to water, right? Water can provide the partial positive hydrogen, and the aldehydes and ketones have oxygens with lone pairs, so they can make hydrogen bonds to water, so that will give it some solubility. But as the carbon chain increases, and the solubility starts to fall off rapidly. So you see the similar with aldehydes. So ethanol or acetaldehyde is infinitely water soluble, so it's miscible with water. But once you go to 3 carbons, then only 20 grams dissolves in 100 mils of water. And of course, as you increase the carbon chain, the boiling point increases as well because there's more surface area, so more van der Waals contacts. Okay, so lastly in this lecture, let's just review the different ways to make aldehydes and ketones, because between organic 1 and organic 2, we've already seen several ways to make aldehydes and ketones. So you can make them from alkenes, if you remember. The reagent, how do you cleave a carbon-carbon double bond? If you remember, that reagent is ozonolysis, ozone. And if the alkene has a hydrogen on it, if you want to stop it at the aldehyde and not oxidize to the carboxylic acid, then you have to use the reductive workup. So H2O2 would take that to a carboxylic acid, H plus and zinc would stop that at an aldehyde. And the other side, since it's got 2 carbons on the double bond carbon, it's going to go to a ketone. So you can make aldehydes and ketones from alkynes, if you remember that reagent. So that reagent is H2SO4 and water, right? Add H and OH across the double bond, but you need a catalyst, mercury sulfate. So if you remember that, we'll add H and OH across the triple bond to give you an enol, which tautomerizes to the ketone, if you remember that. So this is not the mechanism, just a way to think about getting to the product, move that hydrogen down. So add H and OH first across the triple bond to make the enol, and then move hydrogen down on the double bond up, and now you have the ketone, right? Or if you remember from terminal alkynes, you can make aldehydes. So if you wanted to add H and OH this way, and that would be anti-Markovnikov. How do you add H and OH anti-Markovnikov? So that's right, that reagent. So you do the hydroboration oxidation, but you have a derivative of the, so not just BH3, right? You use this derivative of borane. Okay, so those are all organic 1 reactions. And this semester we've covered several ways to make aldehydes and ketones as well. So you can make this aromatic ketone, if you remember. How do you do that? So back to chapter 17, that would be your Friedel-Crafts acylation. Or you can make them from alcohols. How do you make them from alcohols? So that would be back to chapter 11, where you can oxidize them. So then you just have to remember, if it's a primary alcohol and you want to stop at the aldehydes, you need one of the weak or mild oxidizing agents like PCC, PDC, Swerin oxidation, DMP. If you use one of the stronger oxidizing agents, it would oxidize all the way to the carboxylic acid. And if it's a secondary alcohol, then it doesn't really matter what the oxidizing agent is, right? You could use any of these mild oxidizing agents, or you could use some of the stronger ones, like potassium permanganate, chromic acid. All right, so any of these. Or sodium dichromate would be the ones that we covered. And you can get there from a carboxylic acid, but it's not a straight shot. It's not a one-step reaction. You would have to go through a sequence of reactions, right? We've looked at how you can reduce carboxylic acids to alcohols. And then once you have the primary alcohol, then you could oxidize it with a mild oxidizing agent. Okay, we'll stop there.